When artificial intelligence tackles mathematics, it doesn't just solve problems, it translates them. This process, called autoformalization, converts natural language math into strict, computer-verifiable formal code. It's the foundation for building reliable mathematical reasoning systems. But here's the bottleneck. When the AI gets it wrong, we barely know why. Current evaluation methods hand out a simple pass or fail, or maybe a vague numerical score. It's like grading a complex proof by just marking it incorrect, without ever pointing out where the logic fractured or how to fix it. That opacity makes debugging nearly impossible, and training next-generation models a guessing game. To fix this, researchers developed FormalRx, a framework that turns auto-formalization evaluation from a black box into a precise diagnostic tool. At its core is the SciError Taxonomy, which dissects translation failures into 28 distinct categories. Instead of treating every mistake as a generic failure, the taxonomy sorts errors across 3 technical dimensions. First, semantic errors. These corrupt the actual mathematical meaning, like confusing a universal quantifier with an existential one, or misusing logical connectives. Second, constraint errors. These violate the problem's boundaries, such as incorrectly specifying a variable's domain or dropping a necessary assumption. And third, implementation errors. These are language-specific quirks, like integer division truncating unexpectedly, operator precedence binding incorrectly, or type mismatches in the formal syntax. By organizing failures this way, the framework does something previous methods couldn't. It doesn't just flag a mismatch. It generates a complete diagnostic report in one pass. It tells you whether the translation is aligned, exactly which error category triggered the failure, precisely where the problematic tokens sit in the formal statement, and even outputs a corrected version that restores mathematical fidelity. The team trained their diagnostic model, FormalRx 8b, on over 56,000 carefully generated examples where specific errors were systematically injected and labeled. When tested, FormalRx 8b consistently outperformed state-of-the-art general-purpose models and specialized evaluation metrics across 4 diagnostic tasks. It achieved high accuracy in spotting misalignments, correctly categorized nearly 71% of complex error types, pinpointed exact buggy segments, and generated syntactically valid corrections at a rate that surpassed even the most advanced frontier models. But diagnosing the error is only half the battle. The real breakthrough happens when you feed that diagnostic signal back into the model. That's where test time scaling and self-refinement come in. Researchers recently ran a controlled experiment to see how AI models handle iterative refinement. They started by having a base model generate 8 possible formalizations for each of 100 math problems. Then came the feedback loop. They compared 2 approaches when a formalization failed. On one side, a binary feedback system. It just said incorrect, no details, no direction. On the other side, a structured feedback system that leveraged the exact diagnostic output FormalRx provides. It specified the error type, highlighted the problematic code segment, and provided a corrected reference. The model was then given up to 3 refinement rounds. The results were stark. With binary feedback, the success rate barely moved, climbing just 2 percentage points over 3 rounds. With structured feedback, it jumped 7 percentage points and stabilized quickly. In fact, the detailed feedback system consistently outperformed the model's initial guesses, while the binary system actually degraded the quality of subsequent attempts. Why the massive difference? It comes down to signal quality. Both systems were equally precise at catching mistakes. The gap was in utility. A binary label gives the model no directional information about what to change. It's like being told you're lost without a map. Structured feedback acts as a targeted editor. It tells the model exactly which mathematical concept was mishandled, and where, allowing it to apply precise corrections instead of sampling blindly. The data also showed a dramatic jump in the compilation rate, climbing from just over 50% in the first round to more than 95% in every subsequent round. That confirms the self-refinement loop reliably fixes structural and syntax issues first, freeing the model to focus entirely on deeper semantic and constraint corrections. To make this process even more robust, researchers use the error taxonomy to generate realistic training data, teaching the system to recognize and repair subtle logical drift before it ever hit real-world problems. This experiment highlights a fundamental truth about refining AI systems. How we communicate errors matters just as much as catching them. As we push artificial intelligence into increasingly rigorous mathematical reasoning, evaluation can no longer be a final verdict. It has to be the first step in a feedback loop. By connecting every failure to a specific cause and a concrete correction, we can systematically trace weaknesses, refine training pipelines, and iteratively build models we can actually trust. The future of reliable AI math isn't just about bigger models. It's about smarter diagnostics and tighter feedback loops.